Good morning to everybody. I am Francesco Salvestrini and I am a postdoc in Arcetri in Florence. And today I will present a study which is an ongoing study. So we have only results that have to be confirmed on the several ALMA dataset of two nearby Seyferts galaxies. So, okay. This, in order to provide a bit of a context, what I am interested in is the coevolution between AGN and host galaxies, because both the accretion of matter onto the supermassive black hole and the formation of new stars in the galaxies compete for the same gas reservoir. Both processes are able to accrete matter and to provide a feedback on the gas reservoir, and so to affect the properties of the gas. In particular, in this context, thanks to ALMA, we are able to study the molecular gas and its property. And in this work, as well during my career, I mostly focused on the effect of AGN activity on the molecular gas. How we can measure the effect of molecular gas or the effect of AGN activity on the molecular gas? Well, there are several ways. And for instance, we can model the excitation of the molecular gas, because as has already been observed in several galaxies, in order to reproduce the so-called CO spectral line and distribution, especially for high J transition as the high J transition of the CO emission, we need to account for strong radiation fields as the so-called X-ray dominated region, which may be associated to the presence of an AGN in order to reproduce the emission of such high J transition. But the presence of the AGN has been observed as responsible for the presence of molecular outflows, which have been observed both in the local universe and at higher redshift. And what we found is that we found signature in the kinematics of the molecular gas, which are associated with potential molecular outflows, which are a signature of the AGN feedback. And thanks to the high spatial resolution provided by ALMA, nowadays we are also we are able to resolve the feeding processes on the supermassive black hole, and we are able to trace the molecular gas down to parsec scales. And as has already been observed in NGC 1068, we are able to detect the molecular component of the dusty obscuring torus. In this work, I focus on a couple of Seyferts galaxies, which are mid-infrared nearby Seyferts galaxies, and I collected ALMA observation of several emission lines with two goals. On the one hand, to study the kinematics, which is not always easy, because sometimes the kinematics of the molecular gas is not so straightforward, and is not a disk-like, it does not show a disk-like pattern. And on the other hand, by using photoionization code like Cloudy, we model the emission line ratio in order to distinguish between PDR and XDR component. These two objects has already been observed from my collaborators, and in two paper from the past, both galaxies have been observed and studied with Cloudy, and the CO-SLED modeling revealed that there is a need for an XDR component in order to reproduce the CO ladder at high energies, and this suggests that the AGN affect the molecular gas in these objects. These studies have been done with spatially integrated observation, and now we are moving to spatially resolved ones. Starting from NGC 34, we have plenty of emission lines, and in particular, we have two emission lines for the CO, which in particular one, the CO 625 has a very excellent spatial resolution, and we are able to resolve scales of about 25 parsec. And then we have HCO plus the 4-to-3 transition, which is a common use tracer for the dense gas, plus another tracer which have been observed in only few objects in the nearby universe, like the C2H or CCH, which is the ethinyl, which is associated with star-forming gas. All these images are emission integrated images, the moment zero, and they have overplotted the continuum at 1.8 millimeter, which show a spiral-like pattern, which means that there is the dust, which is responsible for this emission, follow a spiral-like pattern down to the scales of a few tenths of parsec. We are also able to estimate the column density of the gas, in particular in the nuclear region, because in particular using the CO625, we are able to measure a column density of more than 10 to the 33, almost 10 to the 34, which is consistent with a heavily obscure nucleus. While when we use shallower resolution of the C322, we measure an averaged column density over a larger region, and these show a lower column density. Moving to the kinematics, we were able to measure the kinematics of the gas, to model the kinematics of the gas by using the 3D Barolo code. And we model a consistent rotating disk with different lines, but we have to put a caveat here, because the C2H emission is not a single emission lines, but is a multiplet. So the kinematical modeling has only been done but in order to see if there is a similar pattern, but it's difficult to interpret this rotating disk because there are multiple lines blended, and so it's not so reliable. But what we can see from the model that are presented on the left with the CO625 and HCO423 is that there is a rotating disk-like motion, and there are some residuals which may be associated with non-rotating gas, which may be the signature of a potential feedback from the AGN, or a feeding, because maybe you are looking at the very nuclear part where there is the feeding of the molecular gas down to the supermassive black hole. Moving to NGC 7130. In this case, we have still the C2H emission line, as well as a low J CO transition, and the same CO625. Here, the resolution is not so good as in the other case, and what we found here is a different picture, because the kinematics is not so good and is not resemble a disk-like kinematics, and what we found here is that a potential depletion of the molecular gas in the nucleus, as we can see clearly in the images of the C2H emission, where the AGN, which is already pointed out in the continuum emission, the emission from the C2H is shallower in the position of the AGN, as well as the CO221 and CO625 is fainter in the AGN, and this is something that has already been observed in several nearby objects, and this is consistent with the potential effect of the AGN activity on the surrounding molecular gas, with potential outflows which may remove the gas in the surrounding medium, but are not able to affect the distribution of the molecular gas on larger scales. Here, due to the shallower resolution, we measured a molecular gas column density, which are fainter. So here we're not able to model the kinematics because it's not a rotating disk-like motion, and so Barolo is not the right code to model it. In order to model the emission layer ratios and using Cloudy, we need to put constraint on the intrinsic emission from the AGN, and the better way to do it is to use X-ray observation to derive the intrinsic X-ray luminosity. For this reason, I study the hard X-ray emission of these two objects, and I obtained an intrinsic X-ray luminosity as well as the column density of the obscuring material in the X-rays. A first result is that, in particular for NGC 34, where we can use the high spatial resolution observation of the CO625, we are able to measure a consistent value on a scale which is likely the one where we are expecting a compact dust molecular torus emission. We are able to measure the column density of the molecular gas, which is consistent with the one measured in the X-rays. This is consistent with what have been observed in the GATOS project led by Garcia Burillo, and where they found that there is a correlation between the column density of the scouring material observed in the X-rays with the one observed with ALMA. So, moving now to the modeling with Cloudy, this is a very simple model, and we are working on more complex model where we use on a PDR and XDR. For the moment, we avoid shocks, which were not included, were excluded from the best fit of the previous studies for my collaborator on a spatially integrated CO sled of both galaxies. Here, I will drive you through these plots, which may be a bit complex. On the right, you have the HCO plus over CO625 emission layer ratio. And we compare now with the color map on the left, where we have on the first row what we expect as a line ratio for the PDR on the upper row and the XDR in the bottom row, depending on the volume density on the x-axis of the gas, and on the y-axis we have the radiation field, PDR on the top and XDR on the bottom.
3 minutes, Francesco.
Okay, thank you. And what we can see here is that we have in the nuclear region, we have an emission which is consistent with both the presence of a PDR and an XDR, but in both cases we need a high volume density for the gas. While we go to the outer region, what we see is that even in the outer region, the presence of the XDR is necessary to reproduce such line ratio. Moving to the C2H emission, in this case, these lines appear not to be produced in XDR region, and so the emission that we see is likely associated with excited by PDR region and non-XDR. For NGC 7113, I show only one example. Here we have also an emission which is consistent with both PDR and XDR, and so we can conclude that for both galaxies we need a contribution for both. In a future also for NGC 7113, we have the same results for the C2H emission, which require only a PDR because the XDR is not able to reproduce such ratio. And so what we can conclude is that for both galaxies there is a need for PDR and XDR, and so the presence of the AGN and its strong radiation field is necessary to reproduce at least some of the emission layer ratios that we see also not only on a spatially integrated scales, but only of sub-kiloparsecs kiloparsec scales. And I also present you the results of the modeling. And so we are seeing a molecular gas rotating disk. And in the next future, I will focus on more complex geometry with cloudy, and also using a couple of molecular gas tracer for shocked region, which may be used in order to include the shock in the cloudy modeling. Thank you.